But anyway, I think we will get started now. 9 is actually a pretty good crowd for something totally optional and during finals week. So yeah, again, what we're going to do is first we're going to go over some stuff from the last test, the test you took yesterday, Monday. Today is Wednesday. The test you took on Monday, we're going to go over things like we usually do. Then I'll go through the stuff that people submitted. I see both of people who submitted things are here now. And then we'll go through new questions as you have them. Cool. So here is the, do you all see my, another statistics slide up right now? Is the correct thing showing? Cool. Okay, so these are the statistics from the most recent test, and this is awesome. So if you remember on test 2 and test 3, the average was only 61. So the fact that it went up by 8 percentage points on this test is really cool. And also this curve of results is kind of shifting over too, like in some of the, so it's shifting towards more people getting higher scores and fewer people getting lower scores. And so even though and that's kind of the trend it's had. Like with test 2 versus test 3, like the average was the same, but it was kind of more distributed for test 2. And then for test 3, more people started getting more higher scores. And now for test 4, even more people started getting more high scores. So that's really awesome. It shows that you have, figured out that you're learning this stuff and that you figured out kind of the way to use geological thinking to answer questions. And also kind of you've figured out kind of you're retaining the information and making the connections and just generally doing really well. And so I think this bodes really well for the final because again, in the final, you are going to be able to use your notes. You're going to be able to use the book. You're going to be able to use Canvas. You're going to be able to use the internet. You are just not going to be able to ask another person, whether in writing or in person. So no posting on a forum to ask, no texting someone, no calling someone, but you can use like pre-existing material. And so, yeah, Google is absolutely okay. You can ask Google. That's part of the internet, but you can't be like, you can't go to a forum for geologists and be like, hey, can you tell me this? Like that is not okay. But if you just ask like, where do you find this kind of rock on Google? Like that's fine. I definitely think though, you're gonna have a better time. Like, I mean, I'm writing the questions based exactly on what we did in this class. So, so like anything where you have to use a chart, it's going to be one of the charts. Like it's going to be based on charts that we used in this class. Like, so it's, so like anything about metamorphic grade or whatever, or about igneous melting or whatever, it's going to be the same charts that we've used before. I'm not going to give them to you on the test because you can find them in your own notes. So part of what the final is going to be is not so much remembering information like the 4 multiple choice tests were, but knowing kind of what information you need to look up, where to go to find it, and how to put the pieces together to tell a geological story. So I'll talk a little more about the structure of the final in a minute, but let's go through some questions from this test first. And so this one, there were actually fewer questions that more people got wrong than right, which is also awesome. It really shows that people were absorbing it and doing well. And so we're just going to go through a few, and there's a couple that like most people got right, but I need to talk about them to explain the next one. But yeah, anyway, this is good. So yeah, yeah. So yeah, so the first question that more people, okay, so this one most people did get right, but I put it up here to motivate the next one. So in this case, it was something like, okay, you have chlorite and amphibole. And so based on this chart, can you tell whether this rock, this protolith, was a sedimentary rock or an igneous rock? So you want to first go up there and go, okay, where's chlorite? Okay, so chlorite's here, but chlorite's also here. So if you just had chlorite, you wouldn't be able to tell. But it says there's also amphibole. And so in this case, amphibole is here. But you notice there isn't any amphibole on this bottom chart. So in this case, we know it's the top chart, right? Because amphibole was only on the top chart. And so then, as you correctly got, this top chart is metamorphism of basalt, which is an igneous rock, whereas shale is a sedimentary rock. So in this case, you only need these two minerals to tell. So most of you got this one right, but does this make sense? Okay, cool. So yeah, so the next question though was, can you determine the metamorphic grade of the rock from the previous question? And so you could say, either it's low, intermediate, or high, or you would need more information to tell. And so the correct answer for this is that you would need more information to tell. And here's why. So I'm going to go back to the other slide. So we're up here, and we're talking about things where both chlorite and amphibole overlap. And so in this case, so chlorite and amphibole overlap in this range. And so in this case, it could be either, so it overlaps partly in the low grade and partly in the intermediate grade. And so in this case, because these are both, it overlaps in both of those categories, you can't tell if you only found chlorite and amphibole, whether this is low or intermediate grade. Does that make sense? So if this were low grade, what other mineral would you need to find to tell this was low grade? Yes, zeolite, exactly, because that one up here overlaps only in the low grade thing. Whereas in the intermediate grade, it honestly would be kind of tricky to tell if something were only intermediate grade, just because garnet doesn't overlap chlorite. So in some cases, you might not really be able to tell, and you would need to look for other evidence. But yeah, so are you good on how to use this? Can I explain why the answer is B for this question right here? So I just did, but I will do that again. The reason it's igneous is because it comes from metamorphism of basalt. And so that requires remembering that basalt is an igneous rock and shale is a sedimentary rock. Does that make sense? Yeah, cool. So like some of these things are going to be like, and so that's the kind of thinking you'll need to do like on the final too, is things like, I might give you some information. I'm going to give you some information. And I'll give you enough information that you can use the stuff, all the charts and all the notes and all the slides in the book and whatever to get the rest of the information. But sometimes it's going to be something like this where like, okay, it's basalt, but like, is it igneous or sedimentary? You have to remember what basalt is. So that kind of thing. And so in this test, of course, you had to just remember that. But on the final, like if you don't remember, you can look it up. But hopefully, like basalt is like the most common igneous rock. Or especially the most common volcanic rock, because the entire ocean floor is made of it. So like if you're going to remember an igneous rock, like basalt and granite are the ones that are most common. Is that clear about both this question and why you need more information to tell whether it's low or intermediate? Cool. Anyone else have any questions about either this or this? Cool. Okay, so the next one, this was actually kind of the only one where a lot of people got it wrong. Like most of them were pretty close. So which of the following is not an example of ductile deformation? So who remembers what ductile deformation actually is? Yeah, so it's stretching or flowing or changing shape. Yeah, so stretching is one part of it. Folding, squishing, distorting, anything where the rock is changing its shape in a way that is flowing rather than breaking. And so in all of these cases, so tilting of sedimentary beds isn't actually changing their internal shape. It's just changing the angle they exist at. So usually when you get tilting, it's because something is like pushing it out of the way. Something might be pushing up or pulling down. Usually when you get tilting, it's because something else is moving and then it's changing its position because of that. So tilting is just a change of position, whereas foliation is a complete restructuring of the minerals in a metamorphic rock. Folding is, folding is stretching and distorting and changing shape. And rock flowing in the mantle, if rock is flowing, by definition, it's ductile or plastic. Like if rock is breaking, it's brittle. If rock is flowing, it's ductile. Tilting is neither breaking nor flowing, it's just moving. Does that make sense? So like if those sedimentary beds were folded, like were a kind of thing where you found, because if you remember, sedimentary rocks always form in flat layers, or clastic sedimentary rocks do. And so if it were a fold, if it were like an anticline, say, where you had a hinge at the top and the limbs pointing down, you would see maybe sedimentary beds at angles, but they would come together to show they were a fold. But definitely you can have things that are not actually internally deformed at all and just pushed into a different position. And so that would be what tilting is. Yeah, you're indecisive on B and D. So it's good to hear that was a close one. But yeah, the key word here is that if something is flowing, flowing is always ductile. Like rock is solid. If solid rock is flowing, then it's ductile. Like always, 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 always. And any other questions about that? Okay, so this next one. So you all did really well on identifying the strike of the fault, on identifying which side was the footwall. Like you all did super well on those questions. But the question here is the left side of the fault moves up relative to the right side. So in that case, so you got that this was the footwall, which means that the other side is what? Yeah, so this is the hanging wall. And so if the hanging wall is moving up, what kind of fault is it? I mean, I guess the answer's down there right now. But yeah, so if the hanging wall is moving up, it is a reverse fault. That's just, and so you might go, well, if it's moving up, it's moving forward. Why is it called that? And it's just because, again, the names come from the fact that the people who named these things were coal miners in the UK. And most of the faults that exist there are normal faults. They're related to extension, where the hanging wall is moving down. And so because those were the most common, they were like, oh, that's normal. And so when they found one that went the other way, they called it reverse. So another name for reverse fault that actually makes more sense in terms of how it's moving is called a thrust fault, because this is the hanging wall is shoving upward and shoving forward. Does that make sense? Yeah, and so the reason this isn't strike slip, if you have something moving up and down, it's not strike slip. Whoops. So if it's moving up or down, you can already rule out anything that's strike slip. So if I said that, imagine the northeast side was moving towards the lower right corner. Like if I said that this side was moving this way, then it would be a strike slip fault, because that direction is talking about a map direction. It's the northeast side. So if it gives you a map direction, you're talking about the strike. If you're talking about something moving up and down, it's talking about dip. So just from something like that alone, you can rule out half of the kinds of faults. And then you just have to think about which direction it's moving in. So in this case, with this example, let's say now that I had that this northeast side of the fault is moving towards the lower right of the screen. What kind of strike slip fault would that be? So imagine you were standing on this side and you watched this fault move. Which way is this side moving relative to where you're standing? Yeah, so it's moving to the right. So then, yeah, so then what kind of strike slip fault is that? Yeah, right lateral. Exactly. So that's how you do that. But I probably, yeah, no, there isn't going to be a question like that on the test. So like on the final. So don't actually. But yeah, just explaining that in the context of this. Any other questions about this one? Cool. By the way, I'm glad that nobody chose D on this question. I would have been upset if someone had chosen D. Anyway, this one. So you were tempted. I'm glad you didn't choose D. Okay, so this one. So the statement there is a 99% chance of a 6.7 or larger earthquake in California sometime in the next 30 years. And so a lot of you said this was a prediction, but this is actually a forecast. And so the difference between a prediction and a forecast is partly that a forecast is well, it is very much that a forecast, other than the fact that we cannot predict earthquakes, we cannot. And you all got that question right. But it's about statistics. So anytime you're talking about a percentage chance, and again, this is a 99% chance of so basically if I were to give a prediction here, I would say like there will be a magnitude 6.7 earthquake in California next week. And that would be a prediction. But in this case, all of these are percentages and ranges. This is a 99% chance. It's saying we think this is very likely, but there's a percentage chance that it might not. It's giving a range, so this is so it's just saying, there will be one of this size or larger. And that's just sort of an arbitrary number they choose to do a calculation with. But yeah, so the chance part is the key. So like when in doubt, read everything super, super carefully. Yeah, so this chance part and this percentage part are really important. And also even this sometime in the next 30 years is also a range. And that seems like a pretty long time. And so this almost seems like a statement that's like, well, is that really useful? But it can be, and very often, like you can't, so this is actually the real earthquake forecast for California. These are the real numbers that come from this thing called the Uniform Californian Earthquake Rupture Forecast, or USERF, because puns for California. I don't know how many of the people involved in it actually surf. I know some of them do. but USERF is a huge, huge, huge statistical calculation. It takes literally everything we know about every single fault in California, and also everything we know just about earthquake physics in general. And they do this massive, massive statistical calculation to just figure out, okay, what's up? Not just how likely is there to be a big earthquake, but also which faults are more likely to have a big earthquake sooner. But anytime it's phrased as a percentage chance of a range of things, it's a forecast. Whereas a prediction would be like, yeah, this is going to happen in this place on this day. And in fact, and also saying it's for all of California is pretty broad. And also for the record, in the last 30 years, in the previous 30 years, between 1990 and now, there have been 9 magnitude 6.7 or larger earthquakes somewhere in California. So this is very much on track with what has already happened. So any questions about that? And of those 9, none of them were on the San Andreas fault. There's a lot of faults that are not the San Andreas fault, but we really didn't have time to touch that in this class. We will talk about that more in both of the classes I'm teaching next semester, though. But anyway, that was actually the last one that most people got wrong. So anything else about test 4 before we start talking about the final? Either about these questions or any of the other questions. It's kind of nice to have time to talk about this. Okay, then if you do think of something, just put it in the chat box or say it out loud. But in that case, we will move on to stuff about the final. So again, there were only 2 people, both of whom are in here, who actually submitted anything to the discussion, to the request box. So if you did think of other things you want me to talk about, just put them in the chat now. But I'm gonna switch gears. So, okay, do you see a slide about plate tectonics now? Okay, good. Okay, so before I get into this though, so one of the requests was actually just to do some practice problems for the final. And that's, so the final is going to be pretty different from the multiple choice tests in that there aren't things that are like, you're not going to be necessarily solving problems in the way that you were for these. So like no 2 questions are going to be exactly alike. So there really isn't a set format or things. Like it's not going to be like you can practice this kind of question several times and then you'll be set for all of the questions on the final. But I can tell you a little bit more about the structure, sort of the way you need to be thinking and kind of the general structure for these. So for the most part, they are not going to be like essay questions. There's like, I guess there's like one of them that kind of is, but for the most part, they really are short answer questions. They're going to be things where it's like you can give a, a sentence or 2 rather than a couple of paragraphs. And so the way it's going to be is like, they're going to be, there are 6 large scale questions, but each one is going to be broken down into multiple parts. And so definitely, so some of them are going to be like, so a lot of times it'll like some of the questions will be like, I will show you a rock. I will give you a picture of a rock and tell you some information about it, and then ask you to come up with some other information about it. So like, things like if it's an igneous rock, like did this erupt out of a volcano or not? Like, is it from a continent or an ocean? Like things like that. And so it'll be things where you can use all of the charts and slides and things to get information about a rock. And so that's often like what geologists really do is like, it's not about like identifying a rock. It's about going, okay, what can I tell about this rock that can tell me about the conditions that formed it? And so some of the questions are going to be things like, tell me some things. I will tell you some things about this rock. You tell me some other things about this rock. And then like, what does that mean about how this rock got like that? And so those will I will break down all of the points really carefully. So it'll be like, for this many points, tell me this, for this many points, tell me this, and so on and so on. So I will be really, really clear about what I want you to answer. And for some of the things, there might be more than one right answer. For some things, like there are multiple ways you could interpret it. And so I'm also just looking for, and some of the questions are actually, some of them are more about like, these are things that happen in a certain way. And some of them are more about like, give me your opinion on this based on what you know. So there's a range of different things. But again, I'm looking for interpretation. I'm looking for just, inquisitive, like investigative geologic thinking, and for your ability to go, okay, in order to know this thing, I need to look this thing up from my notes, and so on. And again, I will be really, really clear about how much each aspect is worth. So be super careful to read all of the parts of the question and make sure you're not missing anything. I absolutely believe in partial credit. I do give partial credit. So even if like you remember the name of the something but don't remember why, or you remember why but don't remember the name of something, just put down everything you do have. I will give partial credit. It is far better to write something than to write nothing. Like even if you have no idea, it is still far better to write something than to write nothing, because I will give partial credit. And also worth noting, okay, so there are going to be 6 questions, but the lowest one will not count. So I still recommend doing all 6. It averages to 20 minutes per question for a 2-hour test. And so I would still do all of them, because sometimes you might not realize how much you do or don't, but hopefully do know about something. So, and then when I'm grading them, I will grade all of the questions and go, okay, that question had the lowest score, so it's not going to count. And then will also be 1 extra credit question. It'll be more of a like, most of the extra credit questions so far have been write me a word or a sentence, but it will require a paragraph probably. And like all the other extra credit questions, it'll basically amount to a 5% point bump, 5% grade bump. So does that answer your question about kind of what to be prepared for? Especially Mario, I know you were the one who asked for that. Are you feeling better about it now? Okay. Yeah, so, and I also will, I see someone connecting to audio. Okay, but yeah, okay, so I will also email everyone all that information again about like how it's going to work, what the timing is going to be like, the reminder to be careful to read everything and make sure you're answering everything. Honestly, the last time I taught this class, the #1 reason people lost points was just not doing all of the parts of some of the questions. So like, make sure you do everything. It matters so much. And then, yeah, I will email everyone about timing, about the reminder, like answer everything. I do give partial credit, like things like that. But any other questions about the structure or how the final is going to work before I get into the stuff from the submission box?
I just got here.
Yeah.
Can you go over like it really quickly?
Okay, so again, 6 questions. Interpretive, like things about I'll give you some stuff and some information, and then ask you to use your reasoning and your notes to find the other information. Most of them will be broken. So even though it's 6 questions, most of them will be broken down into like part A, B, C, whatever. I will say exactly how many points they are all worth. Make sure you do everything. Don't leave anything out. But no, seriously, I will reiterate, like literally the last time I taught this, the #1 reason people lost points on some of the questions was they just didn't do everything. And I know that they had time left. I think they just didn't do everything. So be careful to do everything. I do give partial credit. There are 6 questions. The 5 with the highest score will count, but still do all 6, because you might not realize how much you know about something. And I will email everyone with more information before Monday. So,
Thank you.
Yeah, one more thing. I will be having this one submitted as a file upload. So rather than having you type the answers directly into Canvas, this one I would rather you type it as a separate document and upload it, because that actually, Canvas doesn't like the whole thing where you drop the lowest graded question. It's trying to set that up was just making me frustrated. So it's easier for me to do it this way. Yeah, like a Word document is great, or a PDF or whatever. And that way also, like, I strongly encourage you to type it just because that's easier to read. But that way, like, if there's someone who I know there are some people who've really been like taking this class on their phone. That'll make it so like if you have to handwrite it, you can take a picture and send it to me. But please, if you have the capacity to type it, just because I know my handwriting is awful and I don't want to inflict it on anyone. So like, please type. Any other structured logistics, etc. questions? All right, so again, if you think of any, just put them in the chat box. And now I'm gonna go on to the other stuff from the submission box. So I got a request to go back over plate tectonics, which is why this slide's been hanging out up here. And then I got a request to go back over just the major points about igneous, sedimentary, and metamorphic rocks. And so I'm gonna do this in a way that hopefully ties it together a little more and also gives you some tips as to like which pages of your notes you want to have extra accessible. And then as you, I mean, feel free to ask more questions at any time. Like if it's a question about the stuff I'm saying now, I will do it right there. And if it's a question about some other thing you want me to go back over, I'll go back over it after I go through these slides. And then for those who have come in late, once I go through the stuff that is in this slideshow, I'll go through the stuff that you're asking in the chat box. Once we've done that, again, you can come and go as you please, and I will just hang out until 4, so people can come in or out with other questions as they so desire. But yeah, I'm going to go over the plate tectonics and rocks, which honestly is kind of the whole class. Let's see if we can do that in like 20 minutes, half an hour. So plate tectonics, way back from the beginning of the semester. So the theory of plate tectonics, remember, a theory is a really, really strong statement in science. So it's not like you get some mad scientist character in a movie or a video game where they're like, I have a theory. It's like, no, they have a hypothesis. A theory is something that is backed up by a ton of information from a ton of different aspects of science that basically, it's usually a very simple statement that explains a whole lot of different observations and effects all at once. So like in this case, the theory of plate tectonics states that the lithosphere, the outer layer of the Earth, is broken up into discrete, rigid plates that move around and bump into each other or separate from each other. They move around and interact. And that turns out to explain so many things. It turns out to explain the shapes of the continents, the shapes of the oceans, why you get earthquakes and volcanoes in certain places, why there are fossils of land animals on both South America and Africa of the same land animals, even though that's a big ocean between them now, why there are glacial striations across different continents, why the rocks in Scotland are the same as the rocks in New York, things like that. All of these really wacky, why there are magnetic stripes on the bottom of the ocean floor. All of these really wacky, separate sounding things, when you just go, okay, yeah, the surface of the Earth is broken up and moving around, it can explain all of those things. And so it took decades of different kinds of observations to bring this theory together. But as of now, it is still the paradigm that we go by. This really explains everything about geology and everything we know about the Earth better than anything else does. And so it's accepted as a theory again, being extremely strong. And so, yeah, the interactions at the edge of the plates are especially where the action is. Like if you're in the middle of the plate, like let's say you're in, Minnesota. Minnesota is very much in the middle of the North American plate. So does Minnesota have earthquakes? Not really. Does Minnesota have, so what kind of disasters does Minnesota have? Or like Michigan, Wisconsin. Think about the upper Midwest. Like, what do they have? They got tornadoes.
I would say snowstorms.
Yeah.
Oh, someone put it in the comment box already.
Yeah, tornadoes, snowstorms. Yeah, those are weather. I mean, they're definitely, those are the atmosphere, not the Earth. The stuff that happens there is not related to the plates moving around so much. Meanwhile, here in California, we have earthquakes, we have volcanoes, we have landslides, we have all kinds of things. Again, the volcanoes are in Northern California. We don't have volcanoes in LA. The movie Volcano is wrong. Really all of the action is at the edges of the plates. And usually those interactions, there's always a lot of force involved, but also it's often quite violent. Like that's where you get the explosions, the volcanoes, the earthquakes, stuff like that. Any questions just about the definition here? Cool. So, whoops, I lost a slide. So the reason this happens, if you remember our, let me see if I can put that slide back in real quick, just because it's easier to talk about this with a slide. And we're not in much of a time crunch. Okay, new slide. Do you see the structure of the Earth slide now? Okay. So the mechanical structure of the Earth, which if you remember is about how stuff moves around, is what drives plate tectonics. So in this case, the plates themselves are in the lithosphere, lithos meaning rock. Technically, most of it's rock, but in this case, it's really solid rock. The lithosphere is the outermost layer, and it experiences mostly brittle deformation. So we can use these other terms to talk about it again now. The lithosphere experiences brittle deformation. It is cold enough and under not enough pressure that most of the time, except in really intense metamorphic situations, it breaks rather than flowing. And so that's what allows there to be different plates that are moving around. But what makes them move around is basically, it's convection. It's basically because the inside of the Earth is boiling, basically. So if you think about like making, ramen or making hot chocolate with a mix, making anything where you have a boiling liquid and you pour something on top of it. And if you've ever looked at that, like you might notice that like as the liquid is boiling, the soup seasoning or the cocoa mix or whatever will kind of drift around on the surface of the boiling liquid. That's kind of what's happening with tectonic plates. So in this case, the inner core is solid because it's under so much pressure that it can't melt. But the outer core of the Earth is a roiling sea of liquid metal. It is molten iron and molten nickel, and it is boiling. And because it is super hot down there, but the pressure at this part of the Earth isn't enough to keep it solid. And so basically this is boiling. It's convecting. Convecting and boiling are the same thing. It's the heat, hot stuff rises, travels along the surface of wherever it is until it gets too cold and then it sinks. Then it heats up at the bottom and goes back up over and over and over. And so in this case, that's happening really quickly in the outer core, which is actually liquid. And then it happens slower in the mesosphere. So mesosphere means middle because it's the middle of the 5 layers. And it is not literally plastic, but this term now makes more sense. If you remember that question we talked about from test 4, it's undergoing plastic deformation, or it's undergoing ductile plastic deformation. And so the mesosphere, even though it's solid, it is still warm enough that it can flow as a solid. So the fast boiling in the outer core drives a slow boiling in the mesosphere. And in that case, the asthenosphere above it, which is also undergoing plastic ductile deformation, it's basically is getting dragged along by, like that soup seasoning or cocoa mix, by the convection in the mesosphere and outer core. And then on top of that, the lithosphere is just hanging out on top of that. And so if the asthenosphere is moving around, the lithosphere on top of it is also sliding around on top of it. But while the asthenosphere behaves like plastic, it is ductile, while if you were to shove some asthenosphere into some other asthenosphere, it would just kind of glorp out of the way. Because the lithosphere is solid chunks, if they bump into each other, they're going to crash. You're going to get a collision. And so basically it's the heat of the inner core boiling the outer core, which is boiling the mesosphere a little slower, which is making the asthenosphere flow around. And then the lithosphere chunks are floating around on top of it and bumping into each other. That's what drives plate tectonics. Does that make sense? Do you all remember? Hopefully that still sounds familiar. Any questions about that? All right. So we got our plates. And so there are lots of them, and some of them are quite large. So the Pacific plate is most of the Pacific Ocean. The North American plate is actually not only all of North America, but parts of Russia and Japan are on the North American plate. It's that large. The Eurasian plate is all of Europe and most of Asia. India is its own plate because it used to be way down near Africa and Antarctica. So you've got a lot of plates, and the general distinction is they can have an ocean on them, or they can have a continent on them. And the reason for why some stuff is ocean and some stuff is continent is you just have different rock in them. These two different kinds of plates have very different properties. Even though they're all lithosphere, even though they're all brittle, even though they're all floating around on the asthenosphere, which is convecting because of the stuff below it, ultimately the difference between ocean plates and continent plates controls how they interact with each other. And so whether you have ocean plates interacting with ocean plates, continent plates interacting with continental plates, or those two interacting with each other, you're going to get really different behaviors because their properties are so different. So, and the difference between continental and oceanic plates is really stark. So like oceanic crust is very thin. Like your oceanic crust is your graham cracker, right? It's a thin, dense thing, whereas your continental crust is the marshmallow, where it's thick and very full of air. And so like an oceanic crust might only be like 10 kilometers thick. It might be 7 miles thick. Like if you were to drill 7 miles through the oceanic crust, the technology doesn't exist to do that. But if you were to do that, if you were to have unobtainium and drill into the earth, you would only have to go down about 7 miles to get through into, they did it in The Core. The Core is such a terrible movie that I love very, very much. As a side note, they brought in the screenwriter, and I think it was the screenwriter and the director of The Core, to a geoscience conference like 10 years ago. And they actually brought them in and like had a whole panel on like science in the movies. And so many people, and they were like, yeah, I mean, here's why I made these decisions to do all of this stuff that's totally wrong, because it makes a better story. And it was a very, very fun panel, and I got a chance to tell the director of The Core, it's like, I love this movie so much. It's so stupid and it's good. And he was like, yeah. But anyway, also even if you were to drill right through the oceanic crust, you would end up in the mantle, not in the core. You would have to go so much further for the core. But anyway, oceanic crust is really thin, and it tends to be quite uniform because it forms kind of like a conveyor belt coming out of mid-ocean ridges. And so it's a very uniform layer of thin, dense, extrusive mafic rock. So oceanic plates, if you remember, who remembers what the name of extrusive mafic rock? Like the specific kind of rock it is.
Basalt?
Yes. Yeah. So it's basalt. Exactly. That's what it is. And so the ocean floor is all that. Meanwhile, in contrast, continental plates are they're thick and fluffy. Their thickness is extremely variable. So they can only be they can only be 10 kilometers thick or even less. There are some places near the California and Baja border that the continental crust is extremely thin. But there are some places like in the Himalayas where it can be hundreds of kilometers thick. And so oceanic crust never builds up like this. It just doesn't have the structure to do that. As we'll talk about, it behaves in different ways. But with a continent, kind of like if you think about an iceberg, or again, if you think about floating a marshmallow in something, if you notice, like more of it there's going to be some of it sticking out above the hot chocolate. I've talked about hot chocolate a lot. It's 80 degrees, but now I want hot chocolate. So more of it there's going to be some sticking out above, or like you think about an ice cube in a glass or an iceberg in the ocean, but there's going to be far more of it sticking down below. So for every little bit that is floating above, there has to be a root sticking down below to maintain how it's floating. So like you might hear the phrase, oh, that's only the tip of the iceberg, because you only see a little bit, but there's way more down there that you haven't even gotten into. That's the same idea with continental plates. And so part of the reason they can build up to be thick and fluffy, though, is their structure. So they are made of intrusive felsic rock. So does anyone, so extrusive mafic and intrusive felsic are opposites. So does anyone remember what the intrusive felsic rock is? What's in your countertop? Please don't say Formica. If you had a rock countertop, what would it probably be? Formica is not a rock. Granite, yeah. So continental plates are intrusive felsic rock. They are mostly granite or stuff that has been metamorphosed from granite. Whereas oceanic plates are all basalt, like by definition. And so these contrasts, both in terms of the shape of these plates, how this is thin and flat and this is thick and fluffy, you can see how they might not interact they would interact in very different ways. And also worth noting is, do you remember, what do you remember about the chemical structure of mafic versus felsic minerals?
Felsic has more iron, right?
Mafic has more iron.
Okay.
So when in doubt, so mafic, mafic stands for magnesium and ferrum. Magnesium and ferrum is iron.
Mm-hmm.
That's why the chemical symbol for iron is Fe. I don't know why we call it iron now, but
I think it was like a Latin thing.
Yeah. And then, well, ferrum is Latin. I don't know. And then felsic stands for feldspar and silica. So mafic has a lot more iron, a lot more metal, and felsic has a lot more silica. So we'll talk more about this in a second. But thinking about those silicate structures, do you remember what the shapes of the molecules were like for the more mafic ones, the ones with a lot more metal, than the more felsic ones, the ones with a lot more silica? Does anyone remember? Yeah, so the mafic ones are more packed, right? Yeah, so the mafic ones have simpler molecules that can pack together a lot more densely, and they form either these individual tetrahedra or chains that cause a very dense, flat mineral structure. Whereas in a felsic thing, there's a lot more silica. The things have a lot more air in them. They stick together in ways that are a lot more complex and less dense. Yeah, so mafic minerals are thin and dense. Felsic minerals are thick and have a lot of air. So doesn't it make sense that a mostly mafic plate would be thin and dense and a mostly felsic plate would be thick and fluffy? This stuff, this planet scale plate tectonics of everything, if all of these giant chunks of rock moving around and interacting with each other, it is all connected. This huge planet scale thing goes back down to the molecular level in terms of why it is like this. Yeah, I mean, this is the kind of connections. It's actually, I'm enjoying going back to this at the end of the class, because if I'd gotten into like chain silicates when I was first talking about plate tectonics in week 1, you would have been like, peace out, I'm gone, screw this. But now I can tie this all back together. And this is like, again, the kind of geological thinking is like, sometimes if you can remember like one aspect of something, it controls a lot of other aspects. So yeah, plate tectonics, it's all about mineral structure. It's all, atom scale things control planet size things. But yeah, this difference between thin and dense and thick and fluffy, the way they interact with each other, controls, like, depending on what's interacting with what, you get very different behaviors. So any questions about this before I move on to those behaviors? Cool. It's so nice to have more time to go through this thoroughly. Anyway, so there are 3 major kinds of plate boundaries. You can have plates that are moving apart from each other, plates that are moving towards each other, or plates that are moving past each other. And so if plates are moving apart from each other, it's called a divergent boundary. To diverge is to move away. So plates are pulling apart, and because they're pulling apart, basically they open up, there's an opening between them where magma from the mantle can become lava once it reaches the surface of the earth. So new rock tends to be formed at divergent boundaries because things are moving away and just letting it ooze on out. So you form new rock there. And so in this case, you get a lot of extension of tensional stress because things are moving apart. And so where you are pulling things apart, you're going to get normal faults. See, this all interconnects too. The kind of metamorphism you're going to get here is probably mostly contact metamorphism because you're letting out molten rock. It's going to bake the things around it. But sometimes hydrothermal metamorphism, because in the ocean, if this happens under the water, it's a mid-ocean ridge. And so you have a lot of super hot water that can engage in chemical reactions with the basalt and metamorphose them. And the volcanoes you get at these tend to be pretty low explosivity because you're just letting this stuff out. Like it doesn't really have to explode out. You're just pulling the ground apart and it's just getting out. Does that make sense? So if this happens between two oceanic plates, it's called a mid-ocean ridge. It's in the middle of the ocean, shaped like a ridge. Yeah, it's because of the space it creates. Like you can't just have an endless hole into the center of the earth. And especially, I mean, that's just not, it doesn't work in terms of physics. But also, if you remember, everything below the crust or the lithosphere is ductile, is plastic, it's flowing. Basically, if you pull open the brittle stuff, the other stuff's just gonna flow out. It fills in the space, just like you can't like cut a space in water. Like if let's say you're on a frozen body of water, like let's say you have the surface of something freeze, but the underneath it is still liquid. If you break that ice, the water's gonna start coming out. So the same idea here, just with lava. Does that make sense? It's a lot more dire when it's lava. Although actually frozen water can kick your ass really bad. Like really cold water can kill you quite quickly as well. But yeah, so if this is happening between two oceanic plates, it's a mid-ocean ridge. If it's happening on a continent, it's called a continental rift. And so in a continental rift, this is what ultimately leads one continent to split into two. And eventually it'll move far enough apart that it becomes a mid-ocean ridge. So every continental rift, if it doesn't fail, will eventually move far apart enough that it becomes a mid-ocean ridge. So this picture here is in Iceland. It's kind of an unusual case of where in here it's on a continent, but it's because the mid-ocean ridge basically just projects across a continent. So this is in Iceland and is an incredibly cool place. And yeah. Any questions about divergent boundaries? So this side is, I think this is the North America side, and this is the Europe side. But yeah. The next kind is a convergent boundary. To converge is to come together. So it's two plates coming together. And in that case, old rock is it either gets compressed, so it takes up less space, or it gets destroyed or recycled back into the mantle. And so in this case, because stuff is coming together, it's compressing. You get compressional stress, you get reverse or thrust faults. You get subduction or regional metamorphism, depending on what's crashing into what. And if it's a subduction zone, you're gonna get really explosive volcanoes. So yeah, if it's a continental plate versus an oceanic plate, the oceanic plate will subduct because it's this thin, dense, metallic thing. It's just going to bend and flex down under the thick, fluffy continental plate. If you have two oceanic plates coming together, it's a matter of which one is older, because that one is colder. Because if it's older, it's been longer since it came out of volcano, so it's cooled down more. And because heat rises and cold stuff sinks, the older, colder one will subduct under the warmer one. And then lastly, if you have two continental plates come together, it's like two semis on the freeway crashing into each other head on. They're going to slam into each other and form huge mountains. You're going to get mountains that are sticking above, but again, with the tip of the iceberg. As high as those mountains stick above the surface where we can see them, the root of those mountains sticking down into the mantle is going to be even bigger. And so those are the situations where you get regional metamorphism, where you get those really high grade rocks. Whereas in subduction zones, you're going to get the subduction metamorphism. You're going to get the blue schists and the serpentinites, but you're also going to get volcanoes. So any questions about? Oh yeah, this picture is in Indonesia, which is like it's like 100% volcano. Indonesia would not exist without volcanoes. Like it's all volcanic. But any questions about this, about convergent? Then our last type of plate boundary is transform boundaries. And this is what we have here in California. This picture is of the San Andreas Fault, which is a right lateral strike slip fault. So in transform boundaries, plates are sliding past each other horizontally. Nothing is moving up or down. Nothing is forming, but nothing is getting destroyed. It's just moving rock around. And so in this case, because a lot of it is side to side, all of the stress is horizontal. It's shearing stress. And so you're going to get strike slip faults, things that are sliding in the map direction rather than up and down. The metamorphism you're going to get here is it's mostly dynamic metamorphism. In this case, it's mostly going to be just from the earthquakes themselves, where the sides of the fault move past each other very quickly and turn those rocks, whatever they might be originally, into mylonites that show that shearing and sliding. And in transform boundaries, you don't get volcanoes because there is no pulling apart, letting lava out, and there's no subduction, bringing water into the mantle to help melt rock through the plate. You just don't get volcanoes. So that's why we do not have volcanoes in Southern California, because we have a transform boundary. The only reason that there are volcanoes in far Northern California is because there's a subduction zone up there. So it's a different kind of plate boundary. But yeah, in this case, it doesn't matter whether it's two oceanic plates or two continental plates, it's just going to slide past itself. That's just what it does. You can even slide an oceanic plate past a continental plate. It's just going to slide. Any questions about that? Cool. So before I move on to the stuff about rocks then, any plate tectonic stuff left? Let's go on to rocks, which we've kind of been hinting at, but yeah. So there are three major groups of rocks that we've spent the entire, we've divided up the class by this. So just to refresh your memory, you've got igneous rocks, which are formed by the solidification of molten stuff. And so the thing that controls igneous rock formation, it's all about plate tectonic setting. It's all about volcanoes. And because of what we just said, it's also all about mineral structure. So the chemistry is everything in igneous rocks. Chemistry controls plate tectonics. It controls volcanism. Different chemicals come out of these different settings. It all ties in. But igneous rocks, more than all the others, you need to kind of understand how different kinds of minerals affect what kind of rocks you get. Then you have sedimentary rocks, which are formed by stuff that has been cemented together, by an accumulation of material that has traveled to a place through some means, piled up and become stuck together. And so sedimentary rocks actually have very little to do with plate tectonics. I mean, definitely they'll behave differently in a place with mountains versus a place that's flat, which does have to do with plate tectonics. But it's really all about the stuff happening on the surface. It's about wind, water, ice. It's about all of those things. And really, like if it's happening below the surface of the earth, it's really not controlling sedimentary rocks much at all. So in that case, it's all about knowing how things move around, how the forces of wind and water in particular carry things around and affect the shape of them and help them get stuck back together. And so while classification of igneous rocks is all about what mineral crystals are in it and how big those crystals are, In sedimentary rocks, it's all about what bits of other rocks are in it, how big they are, what shape they are, how stuck together they are. And then metamorphic rocks form when some other pre-existing rock changes its structure and or chemical composition due to changes in pressure, temperature, or surrounding chemistry. So in this case, it's mostly about plate tectonics because temperature and pressure change due to plate interactions. The deeper down you are, the warmer it is, the more close to a plate collision you are, the more pressure there is. So it's mostly about pressure and temperature, but you can have some kinds of metamorphism where chemical reactions can introduce enough changes to the rock that it turns into something else. So these are our general classifications. I'm going to go through each one a little more, but do you have any general questions here? Also, I'm sorry, my cats are running around like maniacs right now. But we good on this? All right. So igneous rocks, again, they're formed by the solidification of molten rock. And so they're always related to volcanoes, whether they come out of a volcano or cool inside the ground below a volcano. You're not going to get melt that can solidify without a volcano. It's all about that. And in this case, chemical composition, again, is the defining trait. What is in it, whether it's mafic or felsic or intermediate, is going to control what the rock looks like, what it does, what kind of volcano you get, how big of an explosion you get. And so by looking at the chemical composition and structure of this rock, you can tell about the volcano that made it, about the tectonic setting, and about how explosive that volcano was. And so this picture is from Hawaii. This is not a very explosive volcano at all. It's an oozy volcano. And this is all basalt. So yeah, and in general, the more oozy the rock, the more oozy the lava, the less explosive it is. But basically, for your igneous rock questions, this chart is going to be your best friend. Have this chart accessible easily during the final. It will help you because everything in igneous rocks is related to each other. More than any of the others, all of the igneous rock stuff exists on a series of spectra. And so the first one is our mafic to felsic spectrum. Like we were talking about, mafic, magnesium ferric, magnesium and iron, lots and lots of metal, very dense, very dark color, like even the color scale. As you go from more mafic to more felsic, you get lighter and lighter in color. With a lot of other rocks, looking at the color isn't going to tell you much, but for igneous rocks, it tells you a lot. So yeah, the spectra are, as you get more mafic, or as you go from more mafic to more felsic, you go from less silica to more silica. You go from more metal to less metal. As you get from more mafic to more felsic, you go from more dense to less dense. You go from melts and cools at a higher temperature to melts and cools at a lower temperature. You go from less explosive mafic to more explosive felsic. So they're all related because they all go back to that chemical structure. The more silica, the more air, the less dense, the lower melting temperature. The less silica, the more metal, the less air, the more dense, the higher melting temperature. But also it's easier for that to get out of the way because it's not sticky, so it erupts less explosively. Does that all make sense? And have this chart accessible. You will use this chart. Other things on this, the mineral composition, again, like mafic versus felsic. Mafic minerals have a lot of metal in them. And so you've got a lot of pyroxene and olivine and plagioclase feldspar, a little bit of amphibole. And then in felsic stuff, you have some plagioclase, a lot of quartz, a lot of potassium feldspar, biotite, some amphibole. The balance of what minerals you have also is apparent in the rock. And we'll talk more about, actually, I'll go back forward a slide and then go back. So, and these minerals always form in related conditions. Like you're never gonna get a bunch of quartz and a bunch of olivine in the same rock. for these reasons, because olivine is a high metal, simple structure mineral, and quartz is a low metal, complex structure mineral. They just form in completely different situations. And so actually just to that comment, yeah, so Zach says that, or Zachary says it's igneous rock is your favorite. I find like everyone ends up having a favorite, like having one they think is the most interesting, that just the one that they understand the best, but also just sometimes tickles their fancy the most. Like everyone kind of ends up coming out with a favorite. But getting into that thing about minerals though, like this chart also, this chart's called Bowen's reaction series, if you remember that from the study guide, also tells you which minerals can form in the same conditions. And so this is just a temperature-based scale. Pressure doesn't really matter here. Oh, cool. I will get to that after I get through this other stuff, Porfirio. We'll totally do that. Yeah, but so at high temperature, you get the simpler structure, more metal-rich stuff. At lower temperature, you get the more complex structure, less metal-rich stuff. And so the further apart things are on this spectrum, the less likely you are to find them in the same rock. So like your felsic rock, your granite is going to have all of this stuff. It's going to have micas, you know, biotite and muscovite. It's going to have K-feldspar. It's going to have quartz, some plagioclase feldspar. Whereas your mafic rocks are going to have olivine and pyroxene, plagioclase, a little bit of amphibole. But you're never going to have these overlap each other just because they form under different conditions. So, so that's also why the balance of these minerals will be it's very set. Like granite is going to have these things in it. Basalt is going to have these things in it. Also worth noting is that the whether something cools above ground or below ground makes a really big difference in what the rock looks like. So something that cools above the ground is going to cool quite quickly because the difference in temperature between the air and the inside of a volcano is huge. And so those crystals are going to get down to their freezing temperature very, very quickly once they're in the open air. So for the most part, in a lava rock, in an extrusive rock, a rock that has come out of a volcano, you're not going to really be able to see the crystals with the naked eye. So for an extrusive felsic rock, it's just kind of pink. An extrusive mafic rock is going to look black. Intermediate is going to look gray. But if it cools inside the earth, even if it's pretty close to the surface, just so long as it's inside the earth, it's being insulated by all of the surrounding rock, which means that things reach their freezing temperature at a lot slower time. And so the crystals have a long time to form and get large before everything is solidified. So in an intrusive rock, which forms in a magma chamber, which forms underground, you're going to be able to see the different crystals. You're going to be able to see the groups of different minerals. So like in basalt, it's black. Like you don't really see everything. It's just black. But in gabbro, you're going to see some black stuff and some greenish stuff and some white stuff and go, okay, yeah, the black stuff is pyroxene. The greenish stuff is olivine. The white stuff is plagioclase. So you'll be able to see the different crystals much better in something that is intrusive because the crystals have gotten larger. So in this case, like the size of the crystals doesn't have to do with what the minerals are, but like literally everything else does. And every class of igneous rocks, felsic, intermediate, mafic, are going to have both an intrusive and an extrusive version. So does that make sense? So like so if I were to say something like, you find some basalt, tell me a bunch of stuff about it, you'll probably be able to get all of that stuff from this chart. Cool. So anything else about igneous rocks? Cool. I keep going like, oh my gosh, we've got to hurry up. But then I realized we said we were going to go till 4. But again, you don't have to stay the whole time if you can't or don't want to. But I'm just going to keep talking. Moving on. So sedimentary rocks are formed by fragments of stuff that have become cemented together or precipitated from solution. And so these tend to form in places where rock particles pile up, like at the bottom of the hills or in the water. And so in this case, it's the texture and the structure that are the defining traits. Is it pointy or is it smooth? Are the clasts big or small? Are they the same size or different sizes? The texture and the structure of that rock are really the most important way of identifying a sedimentary rock. The specific minerals in sedimentary rocks don't matter that much. You can get these different textures and structures with a huge different range of minerals. And what this tells us about is not about plate tectonics, but about what's happening on the surface, what's happening with the wind, what's happening with the water, and so on. And so in this case, so we talked about 4 classes of sedimentary rocks. Clastic rocks are the largest group where stuff piles up and gets stuck together. Biochemical rocks are consolidated from seashells. Organic rocks are stuff like oil shale or coal. That is stuff that was carbon rich, was once alive. And chemical is stuff like in a cave that precipitates out from a solution that like was in water and then solidified out. I can tell you now, because we spent the vast majority of our sedimentary rock discussion on clastic rocks, and because they're the most common kind, any questions about that I ask you about sedimentary rocks on the final will be about clastic sedimentary rocks. So like be aware that these other exist, but in terms of organizing your notes and studying, be solid on how clastic ones work, because I'll be asking some stuff about that. And so now I'm going to go through some stuff about how clastic rocks work. But is this good? Does anyone have any questions there? Okay, so there's a 5-step process for forming a clastic sedimentary rock. So weathering is when the source rock breaks down into clasts. So like you had a solid chunk of rock that gets broken apart into separate chunks. Then erosion is when those separate chunks, called clasts, break away from their source rock. So if something is weathering, it's still just like hanging out in place. But as soon as it gets separated, it's eroded away. That's erosion. Then transportation is when those clasts get moved a distance, like they get moved away from the source rock towards a new place. And so this is, it's usually the main things that do this are wind, water, ice, or gravity. And both the method of transportation and the distance and speed of transportation affect the size and shape of the individual clasts, which is what we'll talk about in the next coming slides. Then the next step is deposition. It's where the clasts get dropped off. And so that kind of affects what clasts are going to end up in the final rock. But also the depositional environment, the place where this is happening, is going to affect the character of those rocks as well. So if you remember, we ended up talking a lot about like what happens in a fast moving mountain stream versus a slow moving river, what happens at the beach versus at the middle of the open ocean. So those are sort of combinations of transportation and deposition factors. But transportation, things are still moving around. By the time something is deposited, it has stopped moving. And then the last step is lithification, is turning into rock. It's the clasts get stuck back together. So first they get compacted, which means they get squished, and then they get cemented. They get stuck together by crystals of other minerals, usually in wherever environment they're in, kind of fusing things together. And so it's this 5-step process. But really in terms of what controls what the final rock looks like, transportation and deposition are the most important because they're really the ones that affect the shape and character of the clasts and affect what ends up in the place where it gets lithified. So does that make sense? So, and so we classify these things based on how big the clasts are, what they're made of, how pointy or rounded they are they the same size or are they a mix of sizes, and what the cement is. Is it more silica or is it more calcium? But again, the ones that are most, these first 4 are the ones that really are affected most by transportation and deposition. So class size, here's our, it's back. Is this large boulder the size of a small boulder? But it's how big are the grains? And all of these things have really specific, like a boulder has a very specific definition. Sand, silt, pebble, all have very specific definitions. Yeah, it is a throwback. But basically, the longer something is transported and the more aggressive the transportation, the smaller the clasts can get. Because even if you start with something pretty big, if you roll it around a river for hundreds of miles, it's going to break down smaller. But it also says something about the weathering mechanism and the erosion mechanism. If generally the bigger something is broken apart, the more likely it was broken apart by force than by chemistry. But it can be both. But yeah, how big something is says a lot about how long it's been and how far it's been transported, how long it's been in transportation, and how far it went. So for something like actually like at the beach, sand is pretty small. Most of what you form in a beach is sandstone. And so in that case, even if the stuff hasn't actually traveled that far from its source rock, if you consider all of the back and forth of the waves over decades and centuries and stuff, even that back and forth just with the tide and adds up to a really huge distance of transportation over time. So does that make sense? So class size, angularity versus sphericity, how sharp versus smooth. And so in this case, also the longer something has been in transportation, the more smoothed out it's going to get. Because the longer things are moving and getting battered around by wind and water and by crashing into other rocks as they travel, the more and more the hard bits on the edges are going to get smoothed out. So if you find something with very angular clasts, they probably didn't get transported very long or very far because they haven't been moved around enough to kind of smooth out all of the edges. Whereas if you find something that's very rounded, it definitely spent a longer time in transportation because all of those points have been smoothed out. So in this case, like the difference between a breccia and a conglomerate is just that the breccia's clasts are very pointy and the conglomerate's clasts are very rounded. So this stuff traveled less than this stuff. That good? Then sorting is how much, what are the mix of class sizes? So something that's very well sorted is going to have pretty much all of the classes are going to be about the same size. Whereas something that's poorly sorted is going to have a big mix of, some very large ones, some very small ones. And so this is also an effect of transportation. So not just on the speed, but also on how variable it is. So generally, if you have a pretty consistent speed, you're going to have different things in different places. Like just so long as if you're just slowing down, like if you're going from fast to slow, you're going to find larger classes where it's fast and smaller classes where it's slow. And so the places where it's traveling very fast, only the big classes are going to fall out, and the smaller ones are going to keep going. And so if you were going to start at the top of a hill in a mountain stream and follow things all the way out to a wide, slow-moving river on a pretty flat area, you'd get more large clasts near the top and small clasts near the bottom, because those small ones are small enough to be carried, even if the water is moving pretty slowly. And so the reason that sorting has less to do with the speed, but more on how variable it is like if you have a situation where like sometimes the water is moving slowly and only small clasts can drop out there, but then sometimes the water is moving quickly and big clasts can drop out there, then you're going to get a mix of things. So a mix of class sizes kind of expresses a mix of transportation speed. So does that make sense? So like a place where you might expect to see a mix of sizes is in a place in like a stream or a river that experiences flooding. So like in a time when it's not flooded, you're going to have smaller clasts depositing because the water's going slower. But in a time when there is flooding, when there's a lot of water moving very quickly, it's going to be able to bring in larger clasts. And so you might get small clasts some times of the year, large clasts other times of the year. So wherever you get variable speed, you're going to get variable sorting. Make sense? And actually, so those are really the main ones for identifying and describing sedimentary rocks. It's how big are the clasts, how pointy are the clasts, how well sorted are the clasts. And so for something like a sedimentary rock, if you can identify things like that about the clasts, you can say a whole lot about how that rock has to have formed. So anything else on sedimentary in general before I move on to metamorphic? And then after I do metamorphic, I'll get to Porfirio's question about minerals forming and getting destroyed. Cool. All right. So the metamorphic rocks, which we've talked about most recently in class, are formed when pre-existing rocks change structure and or chemical composition due to changes in pressure, changes in temperature, and or changes in surrounding chemistry. And so in general, these form in high pressure and or high temperature situations. Even if it is a chemistry thing involved, it still needs high pressure or high heat to make that reaction happen. And so when we're classifying metamorphic rocks, we look at the chemical structure and also like the chemical composition and the structure of the rock. So that's why we were getting at both things like foliation or not, but also looking at things like index minerals, like but also looking at things like metamorphic grade. You know, those are all kind of, they're not as interconnected as in igneous rocks, but kind of one thing can tell us about the other, even if like the presence of, say, epidote doesn't necessarily say much about like how that rock is going to behave when it crashes into another rock. But because temperature and pressure in particular are very much controlled by tectonic setting, metamorphic rocks are again about plate tectonics. Like they ultimately can tell us about what conditions they formed in, where in a plate this happened. So it kind of tells us different things than igneous rocks do. But also, even though this is a high temperature situation, the key thing is that metamorphic rocks stay solid the whole time. It's all about plastic ductile deformation. So this is kind of on the spectrum with igneous rocks in a way, but there's no melting. So high temperature to a metamorphic rock is still too low of a temperature to cause an igneous rock. High temperature means different things in different situations. Sedimentary rocks are low temperature things, like no matter what. But any questions about this definition? And you all did really well on this test, on the metamorphic rocks stuff. So just to reinforce that again, combinations of high heat, high pressure, then also shearing, sliding side by side, and then hydrothermal fluids, chemical-rich, mineral-rich fluids can cause metamorphism. And there were a lot of different kinds of metamorphism that occur under different ranges of these conditions. But for the most part, when you're using charts and index minerals and things to identify metamorphic rocks, they're really on a temperature and pressure axis. You're looking at how hot and how squished. And that really controls most of what's going on with metamorphic rocks. So again, metamorphic grade is just how much the rock has changed from its protolith. Again, a protolith is the rock it started as before it changed into something. And so you can have low grade is low temperature, intermediate grade is medium temperature, high grade is higher temperature. So in some cases, the temperatures for high grade metamorphism might overlap with the temperatures for like felsic igneous rocks, like granite might start to melt, whereas things that are more metal rich might still be going into metamorphic behaviors. So a lot of it depends on the details. But also there's kind of, you might notice there's a couple of different classes of things on here. So contact metamorphism, which is literally just the rock is changing because it's getting heated, it's getting baked by igneous rocks. And so if you think about it, like literally baking, like when you make bread, by heating it, it undergoes chemical reactions that change its structure and exactly what's in it. And it's the same idea here, is like by exposing a rock to something really hot, it's going to bake and change its structure. Meanwhile, but that's usually at pretty low pressure, just because it is mostly about heat. But then you have another class, mountain belt metamorphism, is kind of analogous to that regional metamorphism, that continental collision metamorphism, that crashing two semi-trucks into each other. And so because that involves a lot more pressure, because it's squishing, it's crashing, the temperature range shifts slightly for what's low versus intermediate versus high. Because under high pressure, things can stay solid or stay contained at higher temperatures, because the pressure kind of counteracts the temperature. And then lastly, you have our subduction zones, where you have low temperatures and high pressure. And those always form very specific kinds of rocks. But yeah, it's basically how much has a rock changed. A low grade rock is going to be a lot more related to its source rock, to its protolith, than a high grade rock is. But it's also worth noting that with the metamorphic rock, you can almost never tell just from looking at it what the protolith was, because sometimes the changes are very dramatic. So I am never going to ask you a question like, here is a picture of a metamorphic rock, tell me what its protolith was. I'm not going to do that. That is mean. But I might say, here's a metamorphic rock. It has these index minerals in it. Tell me what its protolith was. So we used this chart earlier today, but again, the same idea of just like, I can tell you some index minerals and you can sort of tell, was it igneous? Was it sedimentary? How high is the metamorphic grade based on what minerals are there? And then based on its grade, you might be able to tell me something about its temperature and pressure. And then also, if you can tell me something about its temperature and pressure, you might also be able to tell me about its tectonic setting. So the metamorphic facies tells a little bit more detail. So while grade is just how much has it changed, facies says more about what has it changed into. So like grade is just like low grade changed a little, high grade changed a lot. Facies is like at a low grade, it turns into green schist or hornfels. At high grade, it turns into granulite or other hornfels. So does that make sense? So how much has it changed? What has it changed into? What can the minerals in it tell us about how much it has changed and what it's changed into? How does what is it changed into tell us about the tectonic setting under which that change occurred? So for metamorphic rock stuff, have all three of those charts handy, because they all are related to each other, even if they don't say quite the same things. So that's any questions again about metamorphic stuff? Or about any of those things? Right. Then that's it for the slides I prepared. So now I'm going to get into taking questions in the chat box. So I've already got a question to go over mineral formation and destruction. So give me a minute to pull up those slides. But now's your time. If there's other stuff you want me to go over again, just put it in the chat box and I'll get to them in the order that they are asked. But I'm going to find that other slideshow now. Okay, so do you see this thing that says rocks versus minerals now? Cool, okay. So this is exactly the lecture slides. I didn't prep new slides for this part because you just asked. So how do minerals form? Again, there's I will go back over earthquakes after we do this, absolutely. So how do minerals form? So they can solidify. So just like how ice forms when you cool water down enough, how basalt forms when you cool magma down, or where igneous rocks form when you cool magma down. The reason that or lava down, the reason that you're getting that is that the minerals were liquid and they become solid. But by definition, again, a mineral is solid and crystalline. So if it's still liquid, it is neither solid nor a crystal. So technically it's not a mineral, technically it's a bunch of atoms. So in order for something to become a crystalline solid, it has to, solidify, has to become solid. So just like ice freezing from water, mineral crystals freeze from melts. So it's just, it gets cold enough that that happens. So in this case, so this is Lake Michigan, this is Chicago. This was an exceptionally cold winter where the lake frickin' froze. But apparently, by the way, it was colder in Chicago than it was in Antarctica on the day this happened. But with igneous rocks and with minerals, this happens at honestly very hot temperatures, at temperatures of hundreds of degrees Celsius. But it's still ultimately that same idea. 500 degrees Celsius is really cold for an igneous rock. So for a bunch of magma, so it solidifies crystals. Other things you can do is precipitate from a solution. So this is very much how you get like gold deposits in cracks in rocks, or how you get stalactites and stalagmites in caves. This is also part of how you get hydrothermal metamorphism, is where you have a solution that has atoms in it. And those atoms might be equivalent to the composition of certain minerals, but so long as they're liquid, they're not crystals and they're not minerals. But as soon as they can start sort of forming crystals on the edge of something, so like in this example of rock candy, these crystals start to form on this wood stick that was stuck into the liquid, this sugar water solution. And so similarly, like if you have something solid stuck into a solution that has a bunch of minerals on it, those minerals will start to form a bunch of atoms in it. Those atoms can start to form mineral crystals on that solid thing, and then the crystals will continue to grow and continue to grow and continue to grow. You can also precipitate from a gas. It's the same idea. It just requires a much larger temperature contrast. So this pretty much tends to happen in volcanic settings. So this is a volcanic vent with sulfur gas coming out of it. So this gas is nasty. It smells like egg farts. It will kill you. But in this case, because it's going from very hot volcanic vent into presumably pretty cold air, it goes straight from being a gas to forming these sulfur crystals right on the basaltic rock. So all of the atoms that are in this gas just turn into mineral crystals on this cold, solid rock. Similar idea, just more drastic. You can get biomineralization where, in this case, animals with shells will pull atoms out of the surrounding environment and work it into the framework of their shells. I'm not going to ask you a question about this one on the final. Don't worry about this one. Don't worry about that one. I'm not going to ask you about this one either. But the way these things are, they get destroyed is honestly, most of it's just the opposite. So you can freeze ice from water, you can melt water from ice. So the same idea is like you can melt rock into igneous rock, and that is turning mineral crystals back into molten atoms. They are liquid, they are not crystals, so they're not minerals anymore. So anytime you melt something back into magma, you're destroying those minerals. Similarly, you can dissolve something. So this is the opposite of precipitating from a solution, is you can dissolve something back into a solution. So in this case, this antacid tablet starts as a solid that actually does involve crystals. These are basically mineral things. But then as soon as this gets dropped into the water, the fluid actually breaks apart the structure of the minerals in this tablet and ultimately mixes up with the water to make a solution of particles suspended in a liquid. And again, because they're suspended, they're dissolved, they're not crystals anymore. They're not solid anymore. So they're not minerals anymore. Metabolism, I guess the opposite of biomineralization, is rather than animals taking mineral stuff out of the, taking atoms out of the environment and making them into something. In this case, by eating minerals, your body breaks them down. Like when you take your vitamins, you can look at your vitamin tablet and they'll say it has these vitamins and minerals. But then your body breaks them down into other things, and you, the stuff that comes out of your excretory system is not crystalline. I'll leave it at that. Actually, I guess if it is crystalline, you should go to the doctor. And then lastly, you can have chemical reactions. So like rust is a way to break down minerals. It's a chemical reaction between the iron in this mineral and the oxygen in the air, and it turns it into something else. So you've built different. Well, hopefully that's working for you. But yeah, any questions about, does that answer your question, Porfirio? Are you good on on building minerals and breaking them down now? Does anyone else have any questions about that? Cool. So then next I'll shift gears to earthquakes. And again, I'll go through that stuff. If you have other stuff you want me to go over, put it in the chat box. While I'm switching those slides, was there specific stuff about earthquakes you wanted me to go back over?
I don't know off the top of my head right now. I think I had a problem with like folding and things like that.
Okay, so folding isn't earthquakes. So do you want me to go over the deformation stuff or the
I
earthquakes?
think, yeah, I think
Okay.
that's what I prefer.
Okay, deformation. Earthquakes are brittle deformation, and folding is ductile deformation.
Yeah, okay. I think what I meant to say was deformation.
Okay, so I will go over that. But if people do want me to do earthquakes, I will do that after that. I have like 15 PowerPoint windows open right now. Okay, do you see this definition of deformation now?
Yes, I do.
Cool. Okay, so deformation is a change in the shape of rocks in response to stress. Stress is kind of exactly what it sounds like. But there is a more specific definition of stress. The push, pull, or shear the material feels when subjected to force. And so just like you were probably feeling pushed around and pulled thin by your finals, and you are feeling stressed, probably. I know I am. I have so many things to grade. I have 3 other classes besides this one that I have stuff to grade in. I mean, they're 3 sections of the same thing, but that's still a lot of papers. Yeah, we're feeling stressed because we're feeling pushed and pulled and torn and all kinds of things by life, by 2020. We are feeling stress. And so it's very much the same thing that happens in Earth, that happens in rocks, is pushing, pulling, tugging, sliding past each other. Stress is what material feels in response to that. So in this one, like definitely, remember this one by that. And so you can have compressional stress, which is pushing, which is squeezing. And so in this case, by pushing on this block, it gets squished out to either side. Just kind of like how we have our continental collisions. The rock into continental plates squishes up and down above the surface of the Earth and into the mantle. That's kind of what compressional stress does, is it pushes things out either way. Meanwhile, tensional stress is pulling. It's things it's stretching out. Things are getting thinner in the middle and then might eventually break. And so this is kind of like, you remember how I said a continental rift is where like a continental plate starts to break apart and then eventually gets thinner and thinner and pulls apart until you get an ocean in the middle? That's kind of like this. It's pulling and stretching. And then lastly, you can have dragging or sliding stress, which is shear stress. So pushing stress comes from both sides. Pulling stress comes from both sides, but shear stress is actually unidirectional, unilateral. So in this case, it's just pulling, the bottom of this thing is staying still, but the top of it is smearing out. So shear stress is what drags things out and stretches them and pulls them along. So it would kind of be like, again, the example that I tried to do that doesn't work well on the screen, where like you have a book and you just pull it. Oh, it super doesn't. Oh, I just broke this. I just broke the binding on this notebook. You get. It's a very old notebook. I've had this notebook since 2008. But it is. This one is okay. This is newer. See how like if I pull on the pages, they smear out, but the bottom is staying put. That's like shear stress. And so stress can be push, pull, or shear. And then strain is the change in shape in response to that thing. So in that case, like, because you squish, because of compressional stress, stuff bulges up or down, that change in shape is strain. Because of tensional stress, stuff pulls out and thins, that is strain, that pulling and thinning. Because I smeared the pages of that book out, it got longer, that was strain in response to shear stress. Does that make sense? Okay. And then deformation then is just how strain affects an entire landscape. So you can have stress and strain act on a small pebble the size of a small pebble. But in order for it to count as deformation, it's an entire landscape. So again, stress and strain can act on microscopic sized things, but deformation is what makes rifts and mountain ranges and folds and faults and stuff like that. Does that answer your question? Whoops. Yeah. So yeah, you can have, for deformation, you can have stuff move around, you can have stuff rotate, and you can have stuff get distorted. So displacement is brittle. It's stuff that breaks and slides. Distortion is ductile or plastic. It's stuff that flows and bends. And tilting's just tilting. Tilting is just, it's getting moved, usually by something else. So usually one of these other things is happening on some other kind of rock, like either a displacement or a distortion is happening to something else that just kind of tilts or pushes other stuff out of the way. Were there other things you wanted me to go over with this? Keep going with folds?
I remember having problems with naming the different types of, I think, displacement. Like normal, reverse, okay, things like that.
Yeah, so we can go back to that. Actually, let me pull up the older version of this lecture from the last time I taught this class that was ultimately not as good, but had animations in it. Okay. Okay, so okay, do you see an animation of a fault?
Yes.
Okay, so actually before I do that, there are, heck, okay, yeah, that's why that wasn't as good. There are two categories of faults. You can have dip slip faults, which slip along their dip, the dip being the angle that cuts into the earth. And we always classify that by the footwall being the obtuse angle side, the hanging wall being the acute angle side. And actually this animation shows both sides moving, but really it's usually the hanging wall that's doing the moving. And so in a dip slip fault, if the hanging wall is moving down like it is here, it's called a normal fault. And that comes from extension. So can you see how this, at the beginning of this animation, the block is one width, but as it goes on, it gets wider? So that's because these are things that are getting pulled apart. And so in this case, because this is an acute angle and the fault ultimately forms a slope, by pulling this apart, this is just sliding down the hill, basically. It's sliding down the surface of the fault as it moves, as it's pulled apart. Meanwhile, in the other thing, in a reverse or thrust fault, see how, so the hanging wall goes up. And you see how as this moves, the two blocks get narrower? Yeah. So this comes from compression, because if you imagine squishing this, as you squish this, that side is going to pop up. And friggin' COVID, I have some literal blocks that I use for examples. Like when I teach this in person, like I actually had some blocks that I would, pull on or squeeze, but they're in my office, which is not here. But I guess I should either go get them or make a new set. But yeah, can you see how squishing would make the hanging wall go up and pulling would make the hanging wall go down? And then The other kind of fault then is called a strike slip fault. And so the strike is the direction that a fault points on the map. So it's a horizontal movement. So if you notice with this example, nothing is moving up and down, everything is going side to side. And so in this case, like there's no hanging wall or footwall, it's just which side of the fault you're on. And regardless of which side of the fault you're on, the way you define a strike slip fault is by which way the other side is moving. So this example is a left lateral strike slip fault. So like imagine you're standing on this block. As this moves, the road to the other side is offset to the left. See what I mean? But if you also imagine you were standing on this side and looking this way, although it's hard to visualize from this animation, it would still be that the other side is moving to the left compared to where you are. And then similarly, a right lateral strike slip fault is just the other direction. And so the San Andreas fault is a right lateral strike slip fault. Most of the really big faults in California are right lateral strike slip faults. We actually have some of all of the other kinds, because as it turns out, the Earth is a lot more complicated than just whatever the plate boundary is what you get. Everything is so much more complex. Like this, there's a reason this class is 101. Like we scratch the surface, but like every single one of these things can get into a bazillion levels more complexity if you want to. So California actually has all 4 kinds of faults and a subduction zone. But the subduction zone is in Northern California. So, from Humboldt northward. But yeah, we have all 4 of these, but all of the really big faults for most of California are right lateral strike slip faults that form in transform boundaries. So does that answer your question, or do you?
No, yeah, that answers my question. Thank you so much.
I'm gonna switch slides just because that's driving me crazy watching it go back and forth. But we have 10 minutes. This has gone really fast. I'm really glad that this many of you have stuck around this long. So does anyone have anything else they want me to go over in these last 10 minutes? Either about content or about anything with the class or about life, I guess.
I was gonna ask this question and save it for the end of this class, but could you please play one more song on your
I will
violin,
do that
right?
Yeah, I can do that at the very end.
Thank you.
I'll probably have to tune it. But yeah, I can do that at the very end. At 4. But I feel like since I told people I would be here to review science until 4, I'm not going to do that before 4.
Yeah, I understand.
I guess, so for the 10 of you that are, or I guess the other 9 of you that are still hanging out, or maybe it's 8. Do I count as number 10? I do. Okay, for the other 8 of you that are still hanging out, anything else? Like, how are you feeling? Anything else you want me to go over, or just things you're worried about, questions about the class, questions about life, the universe, and everything? The answer to that one is 42. Is water wet?